So, let me just state that let me just state some elementary properties. So, elementary properties. If y equal to a x plus b, C y of t is equal to e power I b t C x of a t. Okay, this is again from definition. Yeah, so if you have independent random variables x and y and z is equal to x plus y, the characteristic function of z is given by the product of the two characteristic functions. Okay. This is similar to the property for moment generating functions, except you have an advantage. What is the advantage? It exists, right. So, if I mean the same thing is true for moment generating function, but if you are dealing with let us say two Cauchy random variables, the moment generating function will not exist, right. So, if you want to figure out if x and y are Cauchy distributed, IID Cauchy distributed for example like that, if you want to figure out what the sum is like, right, you cannot use moment generating function, but you can use characteristic functions, right. So, in particular you can do this example for yourself. If x and y are independent and identically distributed according to the Cauchy distribution, you know its characteristic function. So, if z is equal to the sum of two standard Cauchy distributions, its characteristic function will be e power minus twice absolute t, correct. So, you would imagine that, so if you invert that characteristic function, you would imagine that you will get another what kind of a, so it will be another Cauchy distribution with a different parameter, right. So, what I am saying is that you will multiply this characteristic function of x and the characteristic function of y is the same thing, right. So, the characteristic function of z will be e power minus twice absolute value of t, right, which looks of the same functional form, right, it looks like e power minus a absolute t, and therefore, z must also be a Cauchy distribution with parameter square root of 2, right, correct. So, using characteristic functions you can figure out that sum of two independent Cauchys is also a Cauchy, which you cannot figure out using moment generating function. So, the proof of this is straightforward by the way, right, it is just from this is just expectation of e power I t z, right. So, z is equal to x plus y, and then this proof is exactly similar to the proof for the moment generating function. So, now you know a new result, you know that sum of two independent Gaussians is a Gaussian. Now, you also know that sum of two independent Cauchy distributions is a Cauchy distribution, and you cannot figure that out using moment generating function, you have to use characteristic functions, correct. So, this Cauchy is also a stable distribution, so called stable distribution, you keep adding independent Cauchys, you keep getting other Cauchy distributions, okay, just like for the case of the Gaussian which we know, right. For the Gaussian case you can use characteristic function or moment generating function because they both exist, no problem. So these two are elementary properties. What else? So you have, okay, so this is not an elementary property, but I will state it without a proof. So if mx of s less than infinity for s in minus epsilon epsilon, then Cx of t equal to mx of it. This is just what I mentioned earlier, right. If you have, see, if your moment generating function is only defined at the origin, then bad luck. You cannot really, I mean, it may be a very, I mean, it may not say much about the density, but if you have if you have the moment generating function defined in a neighborhood of the origin, then you know that some very nice properties kick in, right. The moment generating function is analytic, so it gets defined in the entire complex plane, and in particular it will be analytic on the j omega axis or the j I whatever axis you call it, vertical axis, right. So you can just substitute s is equal to it, and you can get the characteristic function. Okay. So if you have x is normal 0 1, we know mx of s equal to e power s squared over 2, right, and this is true for all s in the complex plane, right. So Cx of t will be equal to mx of it, which will be equal to e power minus t squared over 2 for all t belonging to R. Okay. So the characteristic function of a standard Gaussian is e power minus t squared over 2, right. So it also looks like a standard Gaussian, right, it looks like e power minus, except for the 1 over square root of 2 pi, right. Yeah. So and then you invoke, suppose you invoke this property, right, then you can figure out the characteristic function of, say, let us say if y is equal to sigma x plus mu, right, then y will become normal mu sigma squared, right. In that case your characteristic function Cy of t will be equal to, you apply that rule, right, it will, you will get e power I mu t times Cx of a t, which will be e power minus sigma squared t squared over 2. Okay. I am just using this rule. So that gives you the characteristic function of even non-standard Gaussians, mean, mu, variance, sigma squared. So now that you know this, if you have two independent Gaussians y1 and y2 with parameters mu 1 sigma 1 mu 2 sigma 2, you can show that z, which is the sum of the two, will also be Gaussian with the parameters mu's adding up and the sigma squares adding up, right. So you can get it from here, but this result you can get it using even moment generating function, right, whereas in the Cauchy case you had to use the characteristic function, right, because the moment generating function does not exist. Is this clear? Yeah, so this is I guess not particularly elementary, but we will not prove this. Okay. inversion theorem. So, this is just like the inverse of Fourier transform. Okay. So, it is a highly non trivial theorem, by the way. I will just state the inversion theorem for characteristic functions. If two random variables have the same characteristic function, then their CDFs are equal, are the same. Without proof. Further, if x is a continuous random variable, then the PDF can be recovered from the characteristic function as follows. So, I believe this holds only for all for every x where I believe it holds for every x where f x is continuous. So, if you have, so this is like the Fourier transform inversion, right, except so I guess for the Fourier transform inversion again you are used to writing integral minus infinity to infinity. It is not quite the same as saying the limit t tending to infinity minus t to t. That is because I mean if you write minus infinity to infinity, these two limits can go at different rates, right. So, but this is the correct statement. Okay. So, you have limit t tending to infinity 1 by 2 pi integral minus t to t e power minus I t x c x of t dt. So, this holds. So, this holds where f x is continuous. Okay. And if I remember correctly, so this I do not exactly remember, I believe that if your f x is not continuous, if f x has a jump, then this inverse transform converges to the middle point of the discontinuity, right. This is again from your Fourier inversion theorem, right. That is something I do not quite completely remember correctly, but this holds for points of continuity. If you have discontinuity, the inverse transform converges to the middle point of the discontinuity. Okay. This is a non trivial result. Okay. So, this just says actually again this is something we will not really use so often, right. You will, it is much easier to usually do pattern matching and figure out what the density is, if at all there is a density, right. But this theorem just says, oh, you know what, given your characteristic function you can obtain your density whenever there is a density. Okay. And in cases when there is no density, there is actually a more general way to recover the CDF. Okay. I do not know if I should state that. Yeah, so let me not state that because I do not have that much time. So, the characteristic function is defined even when x is not continuous, and if you are given the characteristic function of a random variable which is not a continuous random variable, you can, there is a way to invert it to obtain the CDF. Okay. Maybe I will put that in the notes. Okay. Let me not spend class time on it. Okay, so this is a very important theorem. So these I will call these defining properties. Okay. So you will very soon realize why these properties are defining properties of a characteristic function. If x is a random variable with characteristic function Cx of t, then property A Cx of 0 equal to 1 and absolute value of Cx of t less than or equal to 1 for all t in R. Okay. This is something you will understand very easily, right? Cx of 0 is obviously 1, it is expectation of 1, right, if you are putting t equal to 0, and I argued that absolute value of Cx of t is less than or equal to 1, correct. I think I did not write it out, but I argued it out. B Cx of t is uniformly continuous on R. i.e. for all t in R there exists a psi of h, maybe I should call it, this is not the conditional expectation or anything, okay, maybe I should call it, I call psi for conditional expectation, right. So maybe I should call it phi of h, okay, phi of h which goes to 0 as h goes to 0 such that absolute value of Cx of t plus h minus Cx of t is less than or equal to phi of h. Okay. So this is the second property. So this essentially says that characteristic function is a continuous function of t, is actually a uniformly continuous function of t. Uniform continuity is a stronger form of continuity. Okay. Uniform continuity implies continuity, but not the other way around. In particular, uniform continuity is exactly what I have said here. Okay. So normally you mean that by continuity you mean that this absolute difference is small as goes to 0 as h tends to 0, right, that is what you mean by continuity. But in the case of uniform continuity, no matter what t you choose, this absolute difference is uniformly bounded by this function phi of h. See, normally you only need that this difference goes to 0 as h goes to 0, correct, but here you are demanding that no matter what t is, you can choose a phi of h such that this difference is uniformly bounded above by phi of h, and this phi of h is a function that goes to 0 as h goes to 0. Okay, in some sense you are saying that this difference itself does not depend on the value of t, right, it is irrespective of the value of t, it is bounded above by some phi of h, right, that is stronger than a continuous function, right, saying more than continuity, it is called uniform continuity. Okay. Cx, the third property is Cx is a non-negative definite kernel, i.e. for any real for any n and real T1 T2 dot Tn and any complex Z1 Z2 dot Zn we have sum over Jk Zj Cx of Tj minus Tk Zk conjugate is greater than or equal to 0. So, this is a property that seems this is a very fundamental property of characteristic functions. It does look a little bit looks a little bit hard to digest in the beginning, right. I will help you parse this. So, what you are saying is that you are considering these complex quadratic forms, right. This is like complex quadratic form. You are fixing some n, alright, fix any positive integer n and you pick any real T1 T2 Tn you want, any complex Z1 Z2 Zn you want, okay. And then you are looking at, so let me put this in a matrix form, so that it is a little bit easier to digest, right. So, you are looking at a matrix in which the ijth entry is Cx of Tj minus Tk. This is the ijth entry of the matrix or jkth entry of the matrix, okay. And therefore, the diagonal entries will be what? Ones, right, they are all ones, because you will have Tj minus Tj which is 0, Cx of 0 is 1, right. You will have ones on this main diagonal, all the diagonal, and you will have these kind of terms on the jkth entry, and then you are essentially what you are doing is, so really what you are doing is that you are taking the z's like that, right, or maybe this is z bars, right, these are all z bars, this is z1 z2 zn, right. You are looking at a quadratic form of that kind, that is what this is, come to think of it, right. And you are saying that for no matter what these Tj's are, no matter what these Zi's are, this quadratic form is always, this complex quadratic form is always non negative, okay, fine. So, is it clear what it says? So, I am saying that this is exactly the same as this. So, you arrange you choose your Tj's and you form this matrix, right. Then this matrix will have, this matrix is a non negative kernel in the sense that all complex quadratic forms are non negative, okay. So, we have to prove this results, right. So, this first bit is easy, isn't it? This is quite trivial, this and this needs some work, okay. So, how am I on time? I am probably, I just have like 2-3 minutes, maybe I will just try and do part B. So, it says 5 more minutes. So, let me just do part B and part C maybe we will do next class, okay. So, I am trying to prove uniform continuity. So, you have absolute value of Cx of t plus h minus Cx of t is equal to absolute value of e power expectation of e power I t plus h x minus e power I T x, isn't it, right. So, that is equal to, I can write this as absolute value of that, right, I think that's right. Absolute value of expectation of e power I t x times e power I t h minus 1, right. Agree with that? H x yeah, sorry, right, correct. Now, this will become, so this you can show is less than or equal to expectation of e power I h x minus 1, correct, because this absolute value will be equal to 1. Okay. So, this is what you have to look at, right. So, this is like, so if you look at this, this is what, so this will be like the absolute value will be like, so if you write e power I h x as cos h x plus I sin h x, right. So, this will become, so absolute value of e power I h x minus 1 is equal to square root of, you can show that this is nothing but square root of 2 minus 2 cos h x, just trigonometric identities, okay. And then this is equal to 2 times the absolute value of sin h x over 2, correct. So, I am just expanding this cos x. So, just the absolute value of a complex number is, you know, is equal to square root of the real part square, imaginary part square, simplify sin square plus cos square equal to 1, you do all that, you end up with this. So, essentially what we are saying is that this guy will be less than or equal to 2, isn't it. So, this is essentially less than or equal to 2. So, this is my, so okay, so this is my, this is what my phi of h is, okay. So, I have to prove that my phi of h tends to 0 as h tends to 0, but as my h tends to 0, so I have to use dominated convergence theorem now. So, I can take the limit inside, right. So, it is a bounded, so it is dominated above by 2, right. So, I can take the limit inside and this guy obviously goes to 0, right, as h goes to 0, correct. So, by dominated convergence theorem we will get the result. That is the step I was missing, okay. So, maybe we will recap this next class, okay. Stop here.